Okay, we're on the hour, and I made it clear that we want to give everybody the right time. So, good morning, good afternoon, good evening, good night, wherever you are around the globe. And in particular, good morning to Francesco Immorlano, who is joining us today from UC Irvine. So, I hope you're enjoying Orange County and the Southern California beautiful environment there. And what I said is that we're not going to do spending a lot of time on introductions. So, Francesca, it's up to you if you want to introduce your team. But otherwise, we get started with your presentation, and the clock is ticking. Go.
Yeah, thanks so much. I'm sharing my presentation and yeah. Okay.
Okay, good. Here we go.
Okay, yeah. Thanks, Dr. Simon, for organizing the event, and thanks to the ADIA Lab for organizing the Best Paper Award. It's an honor for me that my paper recently published in PNAS was selected among the finalists, so giving me the chance to present my work today. This work was conducted in collaboration with a few colleagues from LIPS, MCC, UC Irvine, and Columbia University, and I would also like to thank my supervisors, Professor Piergentin, Giovanni Aloisio, and Stefan Mant for this work. Here is what I will cover today, starting from some context, motivation, and the scientific gap that stimulated our research. We will discuss the key research questions that we addressed, and I will also discuss the transfer learning approach that we implemented together with the data, architecture, and pre-training. Also, the strategy that we propose to validate our approach and the actual transfer learning on the observational data. We will also analyze the results with some comparison to the state of the art and finally some conclusions and also future works. So, first of all, this work deals with one of the most pressing challenges of our time, which is global warming. Over the past decades, we know that there was a huge increase in the concentration of carbon dioxide and other greenhouse gases caused by human activity, with an increase of more than 50% compared to the pre-industrial era. This huge amount of greenhouse gas is translated into an increase of global temperatures, with the latest report from the Copernicus Climate Change Service revealing that 2024 was the hottest year ever, and also the first year where the global temperature exceeded the threshold of 1.5 degrees Celsius. Such abrupt changes in the climate system are making extreme weather events like wildfires, typhoons, hurricanes, floods, droughts more frequent and intense, with huge damages and loss of lives. That's why we can talk about a real climate crisis. And we can also understand why one of the most important pieces of information for governments and policymakers is how much warming we can expect for a given increase in greenhouse gas concentrations over the next decades and centuries. And that's critical for climate adaptation and mitigation strategies. The tools that scientists now use to study the climate system and project global warming are global climate models. They are actual mathematical representations of the climate system on discrete three-dimensional grids. They implement the fundamental laws of physics that are run into each of the grid box, also modeling the influences and the interactions among adjacent grid boxes. But how can a climate model simulate the global warming in the future? Generally speaking, the amount of global warming will depend on the greenhouse gas concentration that there will be. And this, in turn, is strongly dependent on how the society will evolve with the corresponding emissions. That's why climate models are fed with some scenarios based on the so-called shared socioeconomic pathways that are greenhouse gas concentration trajectories described up to 2100 and linked to plausible and realistic way in which the society might evolve. For instance, going from SSP 126, which is the best case scenario that describes a world where there will be strong mitigation strategies and shifts toward clean energy, so a cut in greenhouse gas emissions, up to the worst case scenario, which is the SSP 585, where and that describes a world where the economy will still heavily based on fossil fuels and with a corresponding very high greenhouse gas emissions. They were introduced in CMIP 6, which is this international effort where several climate centers run their own climate model under a predefined set of experiments, and these highlighted in this red box are the ones considered in this work. For instance, these are the global mean temperatures projected by 22 CMIP 6 models from 1850 to 2100 for the scenario SSP 585. We immediately notice that there are some models that project a very high warming in 2100 and other models that project a low warming by that time. This translates into a large spread of more than 4 Celsius degree in the temperatures projected by these models. And this is still true in the other scenarios that we considered in this work, even if the temperatures are lower, and this is expected as one of them describes is associated to different amount of greenhouse gases that there will be in the future. However, current uncertainties are still too large to enable governments and policymakers to develop proper adaptation and mitigation strategies. A few approaches in the scientific literature tried to reduce these estimates, and they have some limitations. Going very quickly, paleoclimate proxies require strong assumptions between the proxy and the actual climate and the actual variable of interest. They use forcings that are different from the recent ones, and they operate on longer timescales than those that we need. Emergent constraints assume linear and univariate relationships between the constraints and the variables of interest, and we know that everything in climate science is nonlinear and multivariate. And other two approaches are the reduced complexity models, the so-called emulators, and the weighting schemes, which are the state of the art, which only use global mean temperature values without resolving the spatial patterns. So this analysis led us to a couple of key research questions. Can machine learning be used to effectively reduce the uncertainty of future global warming estimates while also modeling the regional temperature patterns? So using global maps instead of just global mean values, and how can this be done? The main answer was the use of transfer learning. Transfer learning is a recent branch from machine learning and aims at transferring the knowledge gathered on a previous task to learn and perform a new but related task. It's made up of two phases. The first one is the pre-training, where the model is trained on some source data to perform a task. Then there's the second phase where the model is fine-tuned on the new dataset to learn and perform the new task while exploiting the knowledge acquired during the pre-training. The way the fine-tuning is done in practice is by keeping the first n layers of the neural network frozen and updating during the fine-tuning the remaining ones, which are randomly initialized. The n layers, the number of layers to be kept frozen can vary according to the specific application. It can also be zero, like in our case, where the initial values are initialized from pre-trained weights from the pre-training, and usually a lower learning rate is used to avoid losing the previous information. How did we use transfer learning to reduce the uncertainty? The main idea was to first train our model on simulation data to acquire all the knowledge about the fundamental laws of physics, about the past, present, and future patterns, and subsequently combine this knowledge about the whole time period with the real-world information coming from observations to generate improve the global warming estimates. Concerning the data, we have three sources of data. First of all, the input data of our model is the CO2 equivalent, which measures the impact of different greenhouse gases on global warming in the equivalent amount of CO2. They were simulated by a model, and we have one global mean value per year from 1850 to 2098, and for the three scenarios that I mentioned before. Concerning the simulation, the pre-training phase, the input is the CO2 equivalent scalar values we just mentioned. The target are the temperature maps simulated by 22 SIMIP6 models for the three scenarios that we mentioned. So since a single model generates a simulation for each scenario, we have a total of 66 simulations. The maps are global. We have one map per year representing the average over the year, and the temporal range is still from 1850 to 2098. Concerning the observational data, during the fine-tuning, the input is still the CO2 equivalent scalar values. The output are the temperature maps gathered from the Berkeley Earth Surface Temperature dataset, same coverage and same spatial resolution of the simulation maps. We have one map per year, but in this case, the temporal range goes from 1979 to 2022, because it's the historical period. This is the architecture that we designed and implemented, and it receives the CO2 equivalent scalar value. It is then there's a dense layer, and the output is reshaped. Then there are two convolutional layers, and each one is followed by an upsampling block to reach the size of the target map, which is the one depicted on the right-hand side. We implemented a single DNN for each model and for each scenario, so for a total of 66 DNNs, each with the same architecture. Concerning the pre-training, let's focus on SSP245, just for simplicity, and a single DNN is trained on a single simulation for each scenario. So the DNN, for instance, DNN1, starts from the global mean CO2 equivalent scalar value for a specific year and predicts the temperature map that was simulated by model 1 for the same year. And this holds also for the other models that are trained on the other simulations. So we end up with 22 pre-trained DNNs that actually are emulators, each one of a single model for the SSP245 we are considering. These are the hyperparameters, and in particular the training years are from 1850 to 2098, reserving the validation years between 2070, 2080 for validation purposes. The learning rate is 10 minus 4, and these are the other hyperparameters. Of course, the same procedure is applied for the other two SSPs. This is the results over one of the results over time, and let's analyze just one scenario for simplicity. Here we have the global mean temperatures simulated by the 22 models that we are considering. These are the temperatures predicted by the DNNs over time, and we can see that the temperature patterns are captured by the DNNs over time, showing less variability as expected, as we do not predict internal variability, and also the CNNs actually approximate the mean of the target. But let's remember that we generate the entire temperature maps. So this is the comparison of what the ensemble of DNNs predicted during the validation years. The ensemble is just the average over the DNNs compared to the ensemble of simulations, and we computed the difference. We can see that the differences are pretty low, confirming that the patterns are captured also in space. So the pre-training is concluded. We ended up with 22 emulators, or 66, sorry, so 22 per scenario. And now, before going to the fine-tuning on the observations, as I mentioned, we wanted to give a proof of concept about the performance of our approach even in the future. We don't have a ground truth in the future when we use observations, because they are just historical. That's why we design the validation strategy using the SIMIP6 simulations as synthetic observations in the way that I will describe in a moment. So let's focus again on SSP245 for simplicity, but the same procedure is repeated for the other scenarios. We start from our pre-trained DNNs. They are 22, each on a single simulation. We take one of the simulations out together with the DNN that was pre-trained on, let's say, model 1, which is our synthetic observation. So we remain with actually 21 pre-trained DNNs. Now the goal is to fine-tune these 21 pre-trained DNNs on the historical simulation up to 2022 of Model 1, which is the whose simulation is represented by the blue line, and the aim is to project the temperatures in the future which are as close as possible to the temperature projected by Model 1. The idea is that the DNNs capture the temperature patterns simulated by Model 1 during the historical period and exploit this information combined with the previous knowledge to project consistent temperatures in the future. These are the hyperparameters, and we use a learning rate that is lower than the pre-training phase to avoid losing the information. And again, this process is repeated, taking out all models in all the scenarios. This is the result after our fine-tuning for just one model that was taken out. And of course, there are the other results for the other models. The red line are the global mean temperatures, so our ground truth, basically, the synthetic ground truth simulated by F-Goals F3L. The blue line are the global mean temperatures predicted by the DNNs, and they are averaged across the DNNs with a corresponding uncertainty, which is the blue shading represented and modeled as the 595% range. And this is the uncertainty of the remaining CMIP6 models. We can notice that the DNNs project patterns in the future consistent with the simulations we are with the simulation we are targeting, and also with a reduced uncertainty compared to the remaining CMIP6 simulations. These are the results over space. Here we have the average of temperature maps predicted by F-Goals F3L in the last 20 years of the century. This is the same map, but just with the predictions of the DNNs in the last 20 years of the century, and this is just the difference between the two. And we see that there are some error spots, but the results are pretty good. So now the validation is concluded. So we somehow showed that the performance of the DNNs after the fine-tuning are good even in the future period where we had a ground truth thanks to the synthetic observation. We can go now to the real transfer learning, to real fine-tuning on the observational data. Again, we said that the input in this phase are the CO2 equivalent scalar values. The target are the maps gathered from the Berkeley Earth surface temperature dataset that have the same spatial and temporal resolution of CMIP6 simulations, and the temporal range is the historical period. To model aleatoric uncertainty, which is the uncertainty related to the randomness of the data, we added a noise sampled from a Gaussian distribution with zero mean and standard deviation equal to the uncertainty of observational data to each map. To model epistemic uncertainty, which is the one related to the model uncertainty and to the lack of data, we repeated this process 5 times per each model and per scenario. So we ended up with 330 versions, noisy versions of the observational dataset, actually. So let's see how the fine-tuning on observations was conducted. These are the again let's analyze the approach for SSP245. We start with our pre-trained DNNs, the emulators of the 22 CMIP6 models for SSP245. Then what we do is to consider, for instance, the DNN1, which was pre-trained on the simulation of Model 1, and we fine-tune this DNN 5 times independently on 5 noisy versions of the observational dataset that were generated by adding the noise to each map. Of course, the noise is always slightly different. So, in this way, we end up with the first pre-trained DNN on Model 1. It was pre-trained on Model 1, but it was fine-tuned 5 times independently on 5 slightly different perturbed versions of the observational dataset. Of course, we used these fine-tuned DNNs to project the temperatures in the future. In fact, the training set in this phase is the years from 1979 to 2022. The validation is the 2017 to 2020, and the inference is the following period. We use a learning rate slightly higher than the leave one out, just to take into account that in this case, we have less data because we start from 1979 to 2022. This is, of course, the process I mentioned is repeated for all the DNNs and for all the scenarios, and this is the result after the projection in the global warming future, in the long-term future. The bold red line represents the global mean temperatures that were predicted by the ensemble of the DNNs with a corresponding uncertainty modeled again as the 595% range. The bold brown line are the global mean temperatures simulated by the ensemble of CMIP6 models, so averaged across the models with a corresponding uncertainty. We can notice that the uncertainty is largely reduced compared to the CMIP6 simulations, thanks to the information coming from the historical observations. And we also predict model the year where the 2 degrees threshold set by the Paris Agreement will be exceeded. This is a result that allows to understand why the transfer learning is useful. Basically, we plot exactly the same result as before, plus the projections made by the DNNs that were only trained on observational data, so without transfer learning. We can clearly see that the DNNs with a corresponding uncertainty lack the knowledge about the pre-training, so that they say about the past, present, and future climate projections coming from the climate models, and they project very unrealistic results that align poorly or don't align it well with the CMIP6 projections. This is the comparison with the state of the art, and this is of our results, and this is a result that was reproduced from the IPCC working group one in the 6th assessment report, which is this organization that reports some bulletins about the status of the climate and etc. They basically model the uncertainty in the last 20 years of the century relative to 1850-1900. Our estimate are the ones depicted with the light blue bars. The other ones are some estimates from the state of the art plus the estimates from IPCC, and this is the same uncertainty computed with the unconstrained CMIP6 models. For SSP245, we reported the reduction of uncertainty that we obtained compared to the other works, and we can see that we obtained more than 50% in uncertainty reduction. This trend is confirmed also for the other scenarios and even for, again, SSP370 and 585. We also checked our temperature patterns that we computed in space, because we generate the entire maps over the historical period, and here we considered the validation years, and we plotted the difference between the maps predicted by the average of maps predicted by the DNNs ensemble over the validation years respect to the observations, because they are actually the ground truth. They reflect the reality. And we made the same plot for CMIP6. We highlighted some of the well-known biases in CMIP6 models, and we can see that all of them are heavily reduced by the DNNs. This is the same map, just plotted in each single validation years. This is just averaged over these years. So again, yeah, these biases are appear strongly reduced compared to the counterpart. This is the projection made by the DNNs ensemble in the last 20 years of the century relative to the pre-industrial period. Again, the DNNs and the CMIP6 ensemble predict different spatial patterns in the future, but this does not imply that our results, that we are improving these regional patterns, and as the future's response is still unknown, so we cannot claim this about the future, of course. So now I will conclude with some conclusions and highlighting also the key contributions of our work. Basically, we demonstrated for the first time that transfer learning can be used to optimally combine the knowledge from models, simulations, and historical observations, thus being able to provide reliable global warming estimates for the future with a reduced uncertainty of more than 50% compared to the state of the art. And this has a strong impact because this information, let's say reliable and precise information about the future, are strongly needed by governments and policymakers to develop proper adaptation and mitigation strategies. We were also able to improve the regional patterns as we didn't use just global mean scalar values as previous approaches, but we worked with the global temperature maps. And we found that the value that actually transfer learning brings in is that it allows to exploit the best of the information from the two worlds, that are the fundamental laws of physics that govern the climate system and that are at the basis of climate models and that are run by climate models, with the real, so combined with the real world information coming from the observational data that we used. And also, transfer learning allows to combine the speed of reduced complexity models, the so-called emulators, with the nonlinear modeling of the spatial patterns that are exhibited by, that are simulated by climate models. Concerning some future works that we have in mind, of course, we plan to include the internal variability that at the moment we are not modeling, to try to characterize the extreme weather events, also possibly with higher temporal resolutions than the yearly. We also plan to extend the historical observations to larger time period to have even more data during the transfer learning. We also plan to include other variables, like for instance precipitation and or aerosol as additional input, or even constraints on aerosol forcing to model the uncertainty coming from this forcing in the historical period. We also plan to use or to consider the use of CO2 maps instead of just global mean scalar values. And the use of explainable AI methods to understand which parts of the data is more important or is contributing most to the final result. And we also plan to do some experiments with some bias-corrected CMIP6 simulations, even if this can be at the expense of explainability. Thanks for your attention, and I will be happy to take any questions. Thank you.
Thank you, Francesco. Congratulations. Perfect timing, right on the 30-minute mark. So I would like first to open this up for questions from our reviewers. And so I would like to ask you, ask the reviewers to use the raise the hand button if you want to place a question. Okay, Marcos is up first.
Thank you, Francesco, and thank you for the presentation. Thank you to the authors for this very interesting and inspiring research. You mentioned the use of transfer learning models, and typically this choice is motivated by data scarcity. In that context, there are typically a number of potential pitfalls that occur, such as feature misalignment or overfitting on a small data. Also issues related to bias propagation and so on. So how confident are you that these potential pitfalls have been addressed?
Yeah, it's a great question. Thank you for it. So first of all, for the variable misalignment, we were very careful in merging remapping our observational data to the same spatial and temporal resolution of CMIP6 data. In fact, as I mentioned, maybe we can also go to the slide. We remapped. Just a moment. Okay, yeah. We remapped them to the same spatial and temporal resolution of the CMIP6 simulations because this was a very important aspect. And so we ended up with one map per year, same spatial resolution. Concerning the data scarcity, actually, this was also the motivation of the use at the basis of the use of transfer learning. In fact, the data during transfer learning were like 4 times less than the data that we used actually during the pre-training, because the period is just bounded by 1979 up to 2022. There are observational maps that we gathered even from previous years than 1979, but they were somehow corrupted, so there were a lot of missing values. So we just decided to use the data of the best quality for our transfer learning, given the importance of this phase. Also, concerning the overfitting, of course, this was a concern. In fact, we used a lower learning rate to keep the information from the previous pre-training, and also to avoid, of course, losing the information, and to avoid the overfitting on the data during the pre-training. And also the use of the same input on the same CO2 equivalent scalar input during the pre-training and the transfer learning was also a way proposed in the scientific literature to avoid or reduce overfitting during the transfer learning phase. And also we used a different learning rate between the fine-tuning on real observations and fine-tuning on our leave one out cross-validation, just to take into account the fact that, again, with observational data, we had less years compared to the leave one out cross-validation, where we used the final year up to 2022, but the starting year during the leave one out cross-validation was 1850. So these were the strategies applied to reduce this risk. Thank you.
Let me suggest something, and I know that you're already considering a number of extensions to your paper. One thing that you may want to try is, instead of doing a leave one out, to do a leave n out, n being a number that is sufficiently large, and it would be a function of the faults that you have in your cross-validation. But the general idea here is that you would do a combinatorial leave out. So if you have, let's say, 2 that you leave out, you do a Cartesian product of what you leave out. If you have 3, then, well, you would do a combination of 3 that you leave out. The idea here is that by doing so, you would generate multiple paths. Instead of having a single cross-validated path, you would be able to bootstrap a distribution of your generalization error. And that might give you a better idea of how reliable the model is. And also it's in itself one way of avoiding overfitting, because it is relatively easy to overfit a single path of forecasts. However, to overfit an entire distribution is much more difficult. So that's one idea for you to consider.
Thanks so much.
May I just add?
I wanted to.
Sorry, go ahead.
Sorry. I want to call on Pierre.
Sorry, no, I'll let you finish. Yeah, go ahead.
No, go ahead, because Pierre Gentin wanted to add to that answer, and so I want to give the co-authors the opportunity to support the presentation.
Thanks for the opportunity. What I just wanted to mention is that here we are quite lucky in the sense that we do have a fake realization of the actual climate, where we can do a lot of the hyperparameter tuning. And that's kind of a huge advantage compared to just using going from a data-rich domain, which are the climate models, to a data poor domain, which are the observations. So we really have a way to check those things in this virtual reality, if you will, and that's a way to also test that we are doing a good job in terms of the extrapolation period. And we use just one. I mean, we tested this one out sampling because that was a way to mimic what is actually happening in the real world, where we only have one realization by definition of the actual climate.
Yeah. And we also tested the same strategy. I, of course, haven't the time to show the results, but we also tested the leave one out, excluding the same models that were belonging to the same atmospheric family as the taken out model. So to avoid any sharing of family lineage between the models, and the results were pretty the same after the leave one out cross validation. So just to quick information. Thanks.
Okay, and then there was somebody else want to say something, but then I'm going to move on to Luis Seco, who had his hand patiently up for a while, unless there's room for more on
no problem.
Previous question.
So very, very nice.
Okay, Luis.
Yes, very, very nice. I have a very simple question. What is the source of all your data? You mentioned Copernicus, so I assume there's some from there. Anything else?
So the source was for the CMIP6 simulations. We gathered them from actually from the repository of the SESGF. So where there are CMIP6 simulations are available. The CO2 equivalent data were simulated by a reduced complexity model from, again, 1850 to 2098, so for the entire period. And it produced the global mean, directly the global mean annual scalar values. And concerning the observational data, they were gathered on a monthly basis from the Berkeley Earth surface temperature dataset, which is a dataset publicly available and maintained by the colleagues at Berkeley. And we processed them actually to obtain the annual version, and again to obtain the same spatial resolution of the CMIP6 simulations. We used a conservative remapping to do that, to align the same resolutions, but these were the three sources of data. So again, just ESGF for nodes for CMIP6 data, the Berkeley group for the observational data, and the reduced complexity model for the CO2 equivalent.
Yes. So the CO2 scalar values, they come from where?
They were simulated by a reduced complexity model, basically an emulator of a global climate model, which simulated the effective rotative forcing. Then
So the CO2 simulated data is not coming from sensors.
Yeah, exactly. Also because we needed the values up even in the future, right? Because we needed the input for Thanks. Thanks so much.
Thank you. Yeah.
Okay, are there any additional questions? Yusuf, yes, go ahead.
Thanks, Francesco and team. Quick one on tagging on to Lewis's question. Did you consider validating against other independent observational data sets beyond just the Berkeley data set, particularly ERA5, although not enough temporal coverage, but it seems pretty relevant here to look at.
Yeah. In fact, that's one of the experiments that we plan to conduct in the future in some follow-up works, and we also need to discriminate between the let's say nature of real historical observational data from datasets like again GISTEMP from NASA or Berkeley, so the one that we used, and we will also be careful about the let's say the nature of ERA5, because it's actually a reanalysis dataset, so the models are still included, right, as information in that kind of dataset. Of course, there's the assimilation phase to produce it, so to merge the model simulations with observations. But for a first experiment, we wanted to focus on purely observational data to gather this kind of information and to provide it to the DNNs. Yeah, that's why we decided to do a first experiment with that. We will definitely think of other more sophisticated frameworks building up on this in some future work. Yeah. Thanks so much. Thanks.
Okay, any other questions? I had a question which was more out of curiosity. When the best data were originally gathered and collected, there was considerable controversy around this best data set. And so my question is more out of general interest. I believe this controversy faded away and had been settled through peer review. And I don't know if you know the answer to this, but I just wanted to find out what the current status of the acceptance of the best data set is in the climate community.
Maybe I can answer that if you want.
Yeah, Pierre, go ahead.
Yeah, I'm happy to answer that. So yeah, it's one of the reference data sets now. Also with the NASA GIS record, which is actually next door to Columbia, and we actually we use both of them. So in the end, we use the best data set. There were some controversy, but people actually debunked a lot of that related to, for instance, placement of weather station data and whether there could be some impact, for instance, like of urban environment, because they can be close to airports and things like that. But people really debunked that and showed that there was really minimal impact. So I think it's one of the most well-regarded data sets, that really used as a reference for many of those things. One thing I'd like to point out, and that's one thing we are discussing now as not a direct extension of this work, but potentially to move beyond, is to also use deep learning to improve some of the existing data sets, going back to just the very basic observations as much as we can. So we are thinking about that and moving in that direction to even improve historical record.
Thank you, Pierre. I actually had some tangential involvement about 2010 or so with the best data, but that's anecdotal, and I can tell this at somebody else who's interested at some other time. It's a very interesting story, but we want to move on to science and not politics. And so, any other questions from the audience? Because I think the first 15 minutes were reserved for our review panel. Are there any questions from the general listeners or viewers? Mark Genton, please go
Yes,
ahead.
hi. Yes. Well, thank you very much for a very interesting talk and enjoyed seeing it. If I understand correctly, the data are annual data at 2.5 spatial resolution, right? About 280 by 280 kilometers, which is very, very coarse in space. So I'm wondering whether this or how this method would scale if we go into a much higher spatial resolution. I mean, I'm thinking about, I don't know, 25 kilometers or 3 kilometers in space.
Yeah, thanks for the question. It's an interesting question. We started with a pretty low spatial resolution because our plan was to conduct a lot of trainings because, as I mentioned, we used a single DNN for each simulation, and this number of trainings was even higher, so multiplied by a factor of 21 in the subsequent phase. So this is the main reason why we decided to go first with a lower spatial resolution. Of course, we plan to scale up to higher spatial resolutions because a lot of details will come out of that, and that will be very, very interesting. Also considering other training strategies to be able to speed up the process, like parallelizing the training or something, even if some form of parallelization was used in this work as well, even with this very low spatial resolution, again, because we had a huge number of trainings to perform, and especially fine-tunings in the transfer line, because, as I mentioned, we ended up with 330 noisy versions of the dataset to estimate the epistemic uncertainty. So we conducted a lot of fine-tuning as well. Yeah, thanks. I don't know if Pierre want to add something.
Yeah, maybe if I can add very quickly. One of the limitations that we had was also the spatial resolution of the original climate models themselves, but now we are working quite a bit using generative AI, especially diffusion models, to try to downscale that. And one of the main drivers, especially of the variability we can see in temperature, is topography in particular, so because you have very sharp gradients just based on that. For this work, it's mostly on temperature, but you could also think about, and we're actually thinking about that, about other variables, especially precipitation, which is very important also for climate adaptation. That's a place where you also need to have very proper uncertainty quantification because rainfall can be very sporadic. And that's also where generative AI comes pretty handy.
Yeah, I mean, especially if you go to higher temporal resolution. I mean, annual.
Exactly.
Is
exactly.
Annual.
In fact,
right, thank you.
That's also another point of follow-up. Thanks.
Yeah,
thanks so much.
Okay, thanks, Mark. Your hand is still up. You have more questions, so that's just okay. Any more additional questions here? If not, then I would like to thank Francesco and his team for their presentation and for the participation. And I would also like to thank our reviewers for review, for participating in the process and listening to 5 seminars in the next four more weeks. And I'd like to invite all of you to join the other presentations. They're always on Wednesday at the hour. I think it is whatever time it is. It is 7 p.m. in Gulf Standard Time, 5 p.m. in Central Europe, and I think 8 a.m. on the West Coast. So you can figure it out, and I'll thank all of you for being here, and hopefully I'll see you next week. Good evening, good day. Bye-bye.
Okay,
Thank you so
bye-bye.
much for your
So
time.
much.
Have a
Bye-bye.
nice Easter, okay?
Bye-bye.
Thanks, everyone.
Bye-bye.
Bye.
Bye-bye. Bye-bye.
Bye-bye.